Okay, welcome to example number 19. We have a RC circuit with two resistors, R1 and R2, three switches, a battery, and a capacitor. And we're asked to do several things here. First thing is the capacitor is assumed to be uncharged. So right now, uncharged means that there is no charge on the capacitor. So Q would be 0 here initially. Okay, and we're asked to find out what would be the currents through R1, resistor 1 here, and resistor 2 if switch 1 and 2 were closed. So let's show them closed. So when those switches are closed at, we'll say t equals 0, then this part is positive and this is negative of the battery, and current will flow from the battery positive all the way through resistor 1. And then we have a junction here. But you'll see switch 3 is still open here, so really no current can go through here yet. So that current will come along to this junction and go straight down this path, all the way down through resistor 2, all the way over here and back to the negative terminal. So the current will follow this particular path all the way around the circuit this way. And we're asked to calculate the current that would be through resistor 1 and resistor 2, and we really just have one single loop. So the EMF is equal to the current times the equivalent resistance. And the equivalent resistance is the sum of those two resistors, R1 and R2, which is 6 ohms plus 4 ohms, which gives you an equivalent resistance of 10 ohms. So the current initially at 0 will be equal to EMF divided by the equivalent resistance. That would be 30 volts divided by 10 ohms, which gives you a 3 amp current that is rolling through this particular loop. And now we move on to the next part where switch 2 is then going to be opened and switch 3 is going to be closed simultaneously. And so here we have it, switch 2 open, switch 3 closed, and we're asked to find the current now through resistor 1 and resistor 2 immediately after this has occurred. So, since switch 2 is open, what do you think the current's going to be through resistor 2? Well, there can't be any current going through this branch. So, I2 would be equal to 0 since switch 2 is open. But current through R1 will be still there, but it won't be the same as it was before. If you look through here now, the current is going to get to this junction. None of it's going to go down here. It's going to now follow this external loop along through here. And this capacitor is now going to suddenly start getting charged. Right now, initially the charge is 0. But everywhere along the wire here and here, every part of that wire is going to have charge moving through it, and we'll have a current. So how do we determine what that current would be through this loop here, going this way? We would have to use I equals the EMF divided by the equivalent resistance. But the equivalent resistance is no longer 10 ohms as it was before because we no longer have the 4 ohm resistance. So we use that 30 volts, but now the equivalent resistance is just resistance 1, which is 6 ohms. So since that resistance has now increased, or actually decreased, then the current through resistor 1 is now going to be 5 amps where it was 3 amps earlier. Now we move on to part C, which is asking for the currents through R1 and R2 and the charge on the capacitor after a very long time. So this was just as the switch was open. So this is basically at t equals 0 as soon as we start this part B. So now part C is at t approaches infinity. And so what we're looking for is what is the current through resistor 1 and resistor 2. Of course, the switch is still open for resistor 2, so I2 must still be 0 amps since S2 is still open. But what happens to the current through the first resistor, I1? I1 must have changed. I1 would actually die out to 0 as t approaches infinity, because as the capacitor becomes fully charged, there is no more current that would flow through the rest of the circuit. However, the charge on the capacitor is no longer going to be 0. Over here, the charge was 0 because it was uncharged. But after a long, long time, the charge on the capacitor at, say, infinity will be equal to the capacitance times the voltage across the capacitor. Now, the voltage of the capacitor would be equal to the voltage of the battery. Let me go back and refer to this diagram so that you can get an idea of what I'm talking about. So if you remember Kirchhoff's loop rule, you could look at it as the EMF minus the voltage drop over this, IR, minus the voltage across the capacitor, which is equal to Q over C, would be equal to 0. And so, but after a long, long time, this will die out to 0. This will approach 0, and the EMF will be equal to Q over C. So therefore, the charge on the capacitor will be the capacitance times the EMF of 30 volts. So now let's substitute those values in. We have 25 microfarads times 30 volts, which gives you a capacitance of, or a charge on the capacitor of 750 microcoulombs, both positive 750 microcoulombs on the upper plate and negative on the lower plate. Let me show that up above. Remember that this upper plate of this capacitor is then connected to the positive terminal of the battery, hence it's going to be positively charged, and the lower plate here is connected to the negative terminal of the battery, and so it's going to have a negative charge Q on that. So if we were to sketch the current over time for resistor 1 over a long period of time, let's assume that we're looking at the period where it's already at 5 amps, so it pumps up right straight to 5 amps. And then as t approaches infinity, we have that exponential decrease where it dies out to 0. And so that would be the graph. Of course, it was earlier to that. It was the 3 amps, and I could show that graph, but we're looking at the point where the switch was closed and the capacitor was just starting to charge up and the current was decreasing exponentially. So now let's look at the situation where we look at switch 3 is closed and switch 1 is then opened up. And then switch 2 is closed, and we're going to be looking at the situation where we have discharging the capacitor. So let's reconfigure our diagram to show switch 3 being closed, switch 1 open, and switch 2 closed. So here's switch 3 closed, switch 2 closed, switch 1 open, and so now the battery has essentially been removed from the circuit, and this capacitor is essentially going to act as a battery remember the voltage is not going to be constant because it's going to be discharging, and as the charge reconfigures itself to be 0 charge at the end, then you'll have no longer any current flowing through this resistor. So we would like to calculate the current through R1 and R2 immediately after the switch is closed. So basically at t equals 0, and at t equals 0, the current through the first resistor now is going to be 0 because there can't be any current going through this particular branch because switch 1 is open. So since S1 is open. However, there will now be current that will flow through resistor 2, and it will go now in the opposite direction that it was when it was charging. So it will go in this counterclockwise direction from the positive charged plate of the capacitor to the negative charged plate of the capacitor. And so that current in the second capacitor is going to be equal to the voltage of the capacitor, because this is essentially acting as a battery, divided by resistance of the externally to the capacitor, which is just resistor 2. So we would take that voltage that it's been charged up to. Remember that this was charged up to a voltage of 30 volts earlier. So we have 30 volts divided by the resistance of 4 ohms. And this is going to give us a current of 7.5 amps initially. Okay, and now moving on to this part where at t equals infinity. So at t equals infinity, this is after a very long time. Of course, current 1 is still 0 amps. And current 2 will now die out to 0 once it's been discharged. So capacitor is discharged, and so no longer is there current flowing through it because Q is now 0 on the capacitor. And of course, Q on the capacitor will also be 0 coulombs because it's been completely discharged. And if we were to sketch the current of resistor 2 after a long time, it would start off at 7.5 amps, and it would die out exponentially as well as when it was charging over earlier for resistor 1. The only difference between resistor 2 and resistor 1 would be the direction of the current. In this particular situation, this would be counterclockwise, and earlier over here, this was clockwise. But both of them would be exponential functions of time, and at t equals infinity, there would be no current in that second resistor. So this is current I2 and this is current I1. And that's it for this example.